This is the solution for the second math puzzle. And first thing we're going to do is find the center of this circle, this poorly drawn circle. So a cool way to do this, if you didn't know, is to just line up the circumferences back there, and we'll line up the circumferences over here, and the intersection is the center of the circle. So I'll label that O. So this is how I solved it. It's not the only solution, of course, but anyways, this is how I solved it. So I first just selected a point on the circle for my first point, and I can do this because the circle is rotatable, so it doesn't matter where I put it. So I'm going to choose to put it right here, and that's going to be my A. So now what I'm going to do is draw a vertical line down from A, and I'll use my ruler. Okay, so it should go through the center. So it's my vertical line down through A. So now let's notice something. We have to use a fact about circles that if you need to recap, I have a geometry video about circles. But let's recap something. So really lightly, so I can erase it, I'm going to draw in pencil what happens when the other 2 points are on the same side of this vertical line. So here's the triangle that came. And this is an obtuse triangle because this is greater than 180 degrees, and it does not contain the center. And it turns out that every obtuse triangle won't contain the center. Because why is this? Is because of this. So if it's an obtuse triangle, that means that remember there's a equation. There's a relationship between the angle. Let's call this angle theta, and the arc. So this arc right here that is captured by that obtuse angle, let's call that alpha. And alpha equals 2 times theta. That's a relationship about circles. And we see that if our theta is greater than 90 degrees, then alpha is greater than 180 degrees, which means that it's going to capture more than the diameter. Because 90 degrees would be if a point was here, a point was here, and some point was somewhere else, because then that would be exactly half the circle. So the problem that we get if it's obtuse is that it captures more than half of the arc length, and therefore the center can't be inside because it always stops short. So let's get rid of these pencil marks so we can do the actual solution. So what we know now, what we know is that one point must be on this half of the circle, this half of the arc of the circle, and the other point must be on the other half. So what is the probability that that should occur? Well, the probability that they're both on this half is 1/2 times 1/2. The probability that they're both on this half is 1/2 times 1/2 equals 1/4 equals 1/4. So add these together, you get 1/2. So it's the complement of 1/2. So there is a 1/2 chance that they are on different halves of the circle. That's the first part of our solution. So now we've made it so that they're on different halves, but that still does not necessarily guarantee that we have a solution. For example, what if one's here and one's here? Then we get, I'm going to use pencil again, then we get a triangle that looks like this. And notice that still does not capture the center. It's still obtuse. So we see that any 2 points that lie on the upper hemisphere, if they both lie up here, then it's not going to work, right? Even if they're really close, if they're here and here, it's still not going to capture it because we're going to draw a line here and up and up. So what's the probability that they're both in the upper vertical quadrants? Well, that's going to be 1/2 times 1/2 equals 1/4, and that's not going to work. All these do not work. But what we do notice is that if they're both in the bottom, then it always works. So if they're both down here, let's say, and we draw our triangle, my red is running out of ink, here's our triangle, then it always works, because notice that it's always going to be below this line, therefore it's always going to contain our center point. So what's the probability that they're both on the underside? And we see that that's going to be 1/2 times 1/2, which we keep seeing, equals 1/4, and it always works in that case. And now there's one case left to think about, and let's use a different piece of paper because it'll take a little bit of work. So let's draw a circle again. This is what I used to draw my circles. Draw a better circle this time. That looks nice. I'm going to approximate the center, and we're going to cut it into quadrants. Approximately. Okay, cool. So, so what if one is up here and one is down here? So they're in alternating quadrants. Well, we see that sometimes that's going to work, sometimes it's not. For example, in this example, if we got lucky, it's going to work. See that the center is just captured. But notice if this point was moved up, it would not work anymore. So we have to do a little bit of rigorous math here. We have to think outside the box a little bit, but that's what these puzzles are for. So notice that if we call this alpha, and then we go ahead and draw a line through the center, then anything from, let's use red, anything in that range will satisfy the condition and contain the center. But if it's outside that range, it won't. So this is also alpha, just by geometry. So that means, and the whole segment is pi over 2 radians, right? Because it's a quarter of a circle. So that means that we have to do a probability calculation involving these things. So we're going to use my method, which I used a method which involves splitting up this arc into many pieces, and then I take the limit to infinity. So I split it up into n pieces, so that each piece had an angle measure of alpha over n, or rather pi over 2 over n, because this whole pi over 2 and I had n pieces, so it's equivalent of pi over 2n. And we have to do each individual probability. So let's take I think we should use a different piece of paper. Let's draw a big simulation of just that quadrant. So here's just that quadrant. So it's broken up into n pieces. And so we have to find the probability for this n. So what is that length? Remember we said it was pi over 2n. Okay, then first, what is the probability of even landing in that range in the first place? Well, it's going to be, since there's n ranges to choose from, it's 1 over n. Then what is the probability that remember this is only going to work if it lies in this range right here, in this range, which is also pi over 2n. So the probability that lands in that region is going to be pi over 2n over pi over 2. Simplifying that, we get, this is 1 over n squared. That is the first probability. What's the second probability? So the second probability is if it lands in this range. If it lands in that range, the probability of getting in that range is the same, 1 over n. And the probability that you're going to get in here is actually double of this one. So it's going to be 2 over n. So that equals 2 over n squared. And it turns out that you're going to keep going through all of these n's until you reach the last one, at which point you're going to get 1 over n times n over n, or 1. And you see that that's true because if you get to this point right here, the probability that that you'll get it is all of them, because you can choose this whole range, and any one of them will contain the center. So this is going to be, if we add up our sum, it's going to look at something like 1 over n squared, right? 1 over n squared plus 2 over n squared plus all the way to n over n squared. And we can pull out the factor, and this over here is 1 plus 2 plus all the way to n in the numerator, so I'm going to use the sum formula, so it's going to be n times 1 plus n over 2. This n cancels with this n, and we're left with n plus 1 over 2n. And now, last thing I want to do is take a limit to infinity. So remember I chose n pieces? Well, we have to assume that there's infinite pieces to get the correct probability figure. So we're going to do limit as n approaches infinity of n plus 1 over 2n, and we see that only the n's will matter in the end, and we get 1/2. So we've proven that there's probability equals 1/2, that if it's in alternate quadrants, then we'll get a success. So now we're going to add them. We're going to add up all our probabilities and get the final figure in this box. So first, what's the probability of getting them in separate sides of the circle? Remember we did that, is 1/2. What's the probability? There's two ways to get success then. What's the probability of success given that they're in opposite sides of the circle? So first, they can both be in the bottom, which is 1/4. And again, so let's write this out because it's getting a little messy. Either on the bottom of this. So the true probability equals probability that they're on opposite sides, either left or right, times the probability that they are both on the bottom, so down, down, plus the probability that, again, they're on opposite sides, left, right, times the probability that success given alternate up, down. So one's on the top, one's on the bottom. So now if we calculate this, probability of opposite sides is 1/2. Probability of both down is 1/4. Probability of opposite sides, again, is 1/2. And probability of success given up, down. So first, what's the probability of them being up and down? So remember that's 1/2. Because the probability that they're both up is 1/4, both down is 1/4, so 1/2 is 1 up and 1 down. 1/2 times probability of success given that. So that's going to be 1/2 times the 1/2 we calculated using the limit. So that's going to be 1/4. And if we add all this up, we get 1/4, which is the final answer. If you have any questions about this, if you have any questions on the process, I know it's a kind of long process, then feel free to post comments and I'll address them.